No? So I reckon we could probably get started.
Okay.
Hi, Hannah, are we ready?
Yeah. Can you hear us okay?
Yeah, I can hear you fine. I just have to mute myself.
This? Enter?
Can everybody hear me fine?
Yep, you're coming through clear here.
You must be.
Okay, cool. I don't see how many people are in the room.
There's 7 of us here.
Super. Great. Hello, everyone. I really wish I could be there in person. There were a lot of great talks yesterday and today. And unless anyone had something that was burning a hole in their pocket, we have a few discussion topics on the workshop's web page, which we can kind of go through, unless they've already been settled by the people who posted them. Is Marta here?
Yes.
Yes. And Elisa? I think this was directed at Elisa.
I'm in the room.
Perfect, thank you. Yeah, I'm sorry I can't be there. So I was also curious about this. About how dynamical friction can really be redshift dependent. And kind of what is the redshift evolution of the dynamical friction, especially for the high redshift ones. Maybe I think I mixed up the. Oh yeah, okay. So I don't know if somebody would like to, either Lisa or Marta would like to kick off. Go right ahead. Give an opinion.
Elisa, do you want to start?
Okay. I mean, actually, I brought at some point a question, but then I realized it was so much in overlap with what you brought, Marta, that I removed it. So maybe I can just comment a little bit on my my perception of this dynamical friction phase and all the hindrances that can happen during the first stage of the black hole pairs in spiral, basically. Because I mean, my perception I got also from like a few meetings I've been to recently is that when we had the final parsec problem, so we had troubles in really understanding if the last bit of the spiral, so that the final parsec actually was efficient or not, then the idea was just to put forward triples, because if the binary stays there for long enough, then you get another merger and you have a triple system, and statistically it's kind of likely that at least 2 out of the 3 will merge at some point. So the triples were kind of the saviors for Lisa in a way to still retain our merger rates. But I think now we have a pretty solid evidence that the final parsec problem is not there anymore. On the other hand, it seems like the problem can be a larger scale, and triples, are still sometimes invoked as the saviors of the finalist spiral. But the point is that we have no evidence, and I personally don't think that we can rely on them in really, bridging the kiloparsec bit. And so I just wanted to really put forward this, but I think it's a problem in the, the understanding as a community of this phase, and also maybe discuss a little more about like when triples can be important in this context, and also if triples are not forming because the distance is too large, then how can we merge the binaries? I mean, are they still merging? What should we do to investigate this more? Yeah.
Yeah, let me just say that, Elisa, you completely understood my point. I mean, it's not only this, it's also that in general, at least I am very confused by how binaries can form. And I mean, again, let me say that yesterday you, Pedro, and Melanie, this was covered mostly by Pedro, already made this point. Well, one is, when do pairs form, and when can triples save us? So, I mean, I think that Elisa and I could go on talking, because I think that we love the same type of physics, and we could go on. But if other people want to intervene, we don't want to monopolize the discussion.
Surely. I could definitely sit here and listen as well. I bet y'all know much more about it than I do. I have a basic understanding, I think, of how dynamical friction is kind of generally expected to lead to pairing of like a dual AGN into like a Keplerian binary more properly. I kind of just usually take it for granted, though. I haven't really read into how, or nor have I read, seen, some very convincing simulation that shows this process happen. If you have insight on whether that's, too imaginative or not.
Yeah, so perhaps I can give a brief summary of the literature, not paper by paper, just the basic summary. So back in the day, we thought that galaxies were spherical, and everything was easy. And also we thought that black holes were just like little balls that fell in galaxies. Now we have realized that black holes are not little balls falling in galaxies, because they produce energy, and with their energy they modify the distribution, especially of gas. And this leads to something that is called positive dynamical friction. So in principle, dynamical friction takes energy and momentum from the black hole, and it slowly or fast spirals down to the center of the exponential well. But if this positive dynamical friction acts in the opposite way, so makes the black hole move away. So this is one problem. And the second is that at least for some types of galaxies, that could be either shallow density profiles or asymmetric distributions of mass, or clumpy systems. Again, dynamical friction doesn't work in the usual way we thought it would. And black holes are just staying there at hundreds of parsecs, kiloparsecs, waiting for something to happen. Or they just move away, or they just they wander around trying to find what to do with themselves. And so, I mean, again, my personal problem was that in the last, I don't know, at this point, probably 5 years or so, with the build-up of literature, I just don't know. I mean, I will quote one of my former students saying, I cannot make my black holes grow, and I cannot make my black holes merge. And it's very depressing. So the way I think about it is that probably I'm not understanding something, because we see black holes grow in the universe, and we expect black holes to merge because we don't see that many binaries around. So I wonder what are we missing? And I don't think I'm the only one who feels that there is not a complete understanding of the problem.
Yeah, no, I totally agree with that. I think it's, I mean, Lucio made like a very good point. I think it was Lucio earlier, or I don't know who said that actually, but that we should really try to understand what are the, morphological features of galaxies that really, have that black hole pairs in them, if they can form those bars that, or like strong symmetries or clumps or anything that can really prevent the spiral, or instead is if for some reason when have like a realistic galaxy, then because in the end it's, I think the evidence is that we just have way more stochasticity than we expected. Not that it's definitely impossible to make black holes sync, just it's much more random, this process. So, I mean, my perception is that we should definitely find a statistical approach to really kind of encapsulate this and then use it for instance, semi-analytical models that are that can be predictive for LISA. But before that, we need to know what is the level of stochasticity of those processes, which is a very hard task because in principle you need a lot of simulations. And so actually in Milano Bicocca, we are doing some effort trying to use like more advanced semi-analytical codes to try to, not have an extreme computational cost, but still model the stochasticity. Matteo this morning presented part of that, but it's still really a little part of the entire thing. And I think we probably really need to think together of how to approach this potential, problem in the modeling.
Yeah, to turn this around, if we had a good sample of binary candidates, we could look in which type of galaxies the binaries actually live, because we know that they have overcome the problem. And we go back to the two problems that we discussed yesterday in the pre-LISA room, which is that typically if they're candidates, they're more massive than LISA binaries, and there are not that many candidates. Again, perhaps with LSST Rubin, this sample will become larger. Oh, Maria.
I was wondering whether, let's say, pulsar timing arrays detect the gravitational wave background, how much that will help, since you won't be able to pin down individual galaxies, but you will have evidence that galaxies overcome these problems and end up.
Sorry, may I ask? It's not exactly, it's related. But Maria, if I followed the recent PTA papers correctly, and I'm not an expert, so please forgive me. But I had the impression that at least with the EPTA paper, they discussed that the background is now higher than actually expected. Is this correct?
Well, we don't have a detection yet. We have maybe hints of, maybe the first hints of what will be a detection in the future. And based on that, yes, we can predict an amplitude of the background. If indeed this is the background and it's not something else we see, the amplitude is towards the optimistic side of the models. Yes.
Well, yes, we have binaries. I'm going to say.
Well, let's make a detection first and then we can all say it. So do you think like having a population in that sense will help instead of, because with LSST we will have the hosts as well. But with the gravitational wave background, we will just have a population. We know they overcome the problems. I don't know how easy it is to disentangle the processes and make some quantitative statement about the earlier stages.
Again, not an expert, but I would say that for me, it's at least reassuring. So I literally celebrated when there was the first hint because I haven't wasted the last 20 years of my life. So I think that it does. And with PTA, we have the advantage that yes, you cannot pinpoint the galaxy, but you know which type of galaxy you have overall. I mean, not the details, but usually there's most galaxies. I mean, if we understand something about galaxy evolution. So that will definitely help. What it won't help with, and I think that Elisa was going in this direction as well, is with real where Lisa binaries live, because they're just different galaxies and different redshifts. So we have to be a bit creative. So, I mean, the way I think about it is that if your model, I mean, your meaning the theorist, has a realistic PTA background, then perhaps the modeling of the Lisa binary is not too terrible. If you completely fail with the PTA background, well, perhaps you should revise your Lisa model as well, but it's not necessarily guaranteed that the two approaches are the same. So I mean, I still feel a bit uncomfortable, even, you know, even what it like this, even if the PTA rate is on the optimistic side, I still feel a bit uncomfortable about saying that the Lisa rates will be also on the optimistic side. I don't know if
So I guess there are a lot of uncertainties saying PTAs detect the local massive population, whereas Lisa detects the, I would say, the progenitors and rewind in the history. So I guess I understand your point, yes.
This said, I mean, again, I'm breathing better since the background has been potentially detected.
I think Aaron had his hand up next. Go ahead.
Yeah, I just want to tack onto that because you inspired me with some thoughts. Is that I think it'll help in a way in that a lot of the problems with studies of supermassive dual AGN in these systems is that we have so many biases in how we find these things, and there's just such little completeness. But the thing is, we don't know how incomplete or how biased we are from like a ground truth. We can compare it to, you know, simulations or theory, which is also then just based off previous observations. But gravitational waves would give us a completely almost independent method to look at a rate and then compare that to what we could expect from our biased observations. And that can almost, I think that might be able to give us insight into how wrong we are in that regime, which I think will then give us insight into how wrong we might be in a different regime with its own biases of its own kind. But at least it kind of gives us an idea of if we identify supermassive black holes, our dual AGN, originally by, you know, using a mid-infrared color cuts and X-ray luminosity cut, for example, or, you know, a BPT diagram, and then but we're wrong by this much from gravitational waves, and now we're looking for Lisa regime equivalent using maybe you know, lower cuts but similar methods, you know, maybe using some sort of you know, luminosity function or some sort of population function to compare the two, and then we can say maybe we'll probably be this wrong, even using current observations of, you know, our MBHs instead of SMBHs, and that might be able to get us somewhat of an estimate between biased observations to expected, you know, gravitational wave rates from this different population. Would be something that I think you would be interesting to look at and might be helpful.
Yeah, absolutely. it'll be a give and take for a while, probably. I saw Mateo's hand up for a moment. I don't know if you have a question or a point.
Well, no, yeah. Actually, it was already answered because as Marta, I'm a bit concerned about the statement that after a detection of pulsar timing array gravitational wave background, we could say definitely that Lisa will see a lot of binaries because, yeah, there are still a lot of uncertainties. So, yeah, that was only my comment.
Elisa, did you have a hand up?
Yeah, I mean, we're probably all saying the same thing. Also, I don't want to monopolize the discussion, yeah. So maybe just to add on that. So because in pulsar timing, the black hole masses are very large, right? So the galaxies that are going to be around those very massive black holes, at least if we look at the nearby universe, they are kind of regular, nice, easy to model in a way. So I expect them to, I mean, the dynamical friction, all those processes to work in a much nicer way that we are much more, ready to model right now. On the other hand, the black holes of Lisa are significantly less massive. And so, I mean, I'm totally agreeing with the fact that the PTA detection really gives us a lot of hope that, I mean, at least from a statistical side, I mean, I think we can be more confident of the fact that Lisa is going to detect signal. On the other hand, it's hard to extrapolate on lower masses because, I mean, those stochastic processes, I believe, are going to be much more important in the lower mass and much more irregular galaxies.
And could I ask a really naive question, expose my ignorance of pulsar timing arrays? If there's an expert in the room, I think maybe Maria and Hannah, probably no more. Oh no, so these are the stochastic background is like some, some imposed superposition of like mergers throughout cosmic time, right? But could like an individual binary, like the in-spiral of individual binary, be detected in principle from a pulsar timing array?
Yeah, so the short answer is yes, we expect to detect individually resolvable binaries on top of the background. It's not going to be the in-spiral. It will be a binary that has a specific frequency and it stays at this frequency for pretty much all the time we observe. The reason is that we trace earlier stages of the evolution. And from models, and I think Luke just joined, so he could also chime in, we do expect to find individually resolvable binaries a few years after we detect the background. So it should happen before Lisa flies.
Very interesting. So could this perhaps be informative for this whole dynamical friction confusion?
I think that goes back to the problem that PTAs probe different masses and different types of galaxies. So the same uncertainties are there for the background and for individual sources for linking the rays to Lisa.
I see. Thank you.
Can I ask a naive follow-up question? The individually resolvable PTA binaries, which I know very little about, are they can they be localized to a how well can they be localized? I guess
they're not well localized, and the reason is because we don't see the in-spiral. And I think you have done some work on like how many galaxies there will be in the error box. So it will be hundreds of galaxies. I think the good thing in localizing a PTA source is like they're very massive and relatively nearby. So they're not that common galaxies. So yes, potentially if we put some effort, we can filter it to a few dozens of candidate galaxies and with more effort pinpoint the correct galaxy, but it's not going to be trivial.
Very cool. Are there any more questions, comments, or concerns about dynamical friction before we maybe move on to a different topic for now, at least? Alrighty, take that as a no. There was a second thing on the discussion topics, which it looks like maybe Marta asked a question to Elisa about these out-spiraling binaries and accretion disks, and its dependence on the Eddington fraction. And I just kind of summarize the point, I think. If the Eddington fraction, larger Eddington fraction implies more out-spiral, more likely to out-spiral. But if that means that they're also more likely to be at the self-gravitating radius, so about a larger radii of the accretion disk, and will that also decrease the amount of accretion that's happening? I think it's just the question. Lisa responded and dropped a graph. I did not have a chance to look at the graph. But did y'all have a chance to talk about this and understand?
Okay, so I can just briefly maybe comment about this because I mean, I think the point is very important, meaning that I mean, when we have our binaries expanding in the this ODE solver that we put together, at some point the binary reaches the disk self-gravitating radius, and then we force the expansion to stop because we don't believe, we have no evidence of the binary expanding in the self-gravitating regime. So of course, at this point, the idea is that if maybe also the binary can stop accreting mass, and so in order to really understand if this also plays a role and like it invalidates our modeling, we have made a few runs in which we tried to block the binary out spiral at the self-gravitating radius in the same way in which we block mass accretion. So since this is like, but from the physical point of view, and also numerically implementing the thing, you cannot really say for a binary that is larger than this radius, just stop everything. We had to put a smoother function, like the usual, you know, smooth the step functions, and so that both accretion and expansion are stopped in the same way. And if we do that, the overall time for the binary to reach coalescence changes a little bit, but it's not a dramatic change. So still, the case in which we have expansion and the case in which we don't have an expansion, even if we further assume the binary won't accrete more, much at the self-gravitating radius is still up to about an order of magnitude. And this is in a way also reassuring to us, because it means that even if the binary stalls at the edge of this self-gravitating radius and it can only accrete a little mass, still that would be enough for it to eventually reach the gravitational wave regime and coalesce. I don't know if this is a bit more clear. Actually, I'm a little afraid that people who couldn't follow, maybe also due to time zones in the morning, are not really following this discussion. I don't know how much I meant to summarize the talk of.
Does it help? I'm sharing your figure that you put on the Dropbox Drive. Does that help you explain? Maybe you can clarify this figure.
Yes, well, actually, the right-hand panel that is shown in this plot is the same panel I showed in the morning for those who could follow, just with this additional, capping of the mass accretion of the binary. And basically, you see as a function of the Eddington ratio of the binary, so how much efficiently it's accreting, the time scale it takes to go from the onset basically from the moment it is bound, let's say, all the way down to merger. And you see that the time scale rises when we are close to Eddington limit, but again, it goes down afterwards. And so again, the main message, I think, so even if the binary is not accreting really much at the edge of the self-gravitating radius, it manages to merge within a Hubble time. And anyways, I would dare to say it probably manages to merge over a time scale that is anyways shorter than what is probably going to be its dynamical friction time scale. So this is probably anyways not going to be the bottleneck to coalescence. But I mean, if this was not clear, just ask. I don't know if this is more clear for Marta, who actually asked the question. I hope.
Yeah. Okay. So I will ask my question. So here, what you read on the x-axis is the initial Eddington ratio of the binary.
It's kept constant. So as the mass of the binary grows, also the mass accretion grows, so that the Eddington ratio is kept constant throughout the whole run. This is the right-hand plot.
Okay, so I don't. So when you say that you cap the accretion or at the self, I don't understand what you're actually doing. I'm sorry.
Oh, okay. Yeah, I mean, this can get a little bit technical, but basically what we have is that this binary at some point can start expanding, right?
Mm-hmm.
When it expands, at some point we have, like, when it reaches this famous self-gravitating radius, we don't allow it to expand any further.
Yes.
Just because, okay, what I said before. So the plot I showed in the morning would assume the binary to stop expanding at that radius, but keep accreting at Eddington, at this fraction of the Eddington limit. Instead, this plot shows the case in which, as we reach the self-gravitating radius, also mass accretion is stopped, basically.
Okay. Okay, when you say capped, it's really stopped.
Yeah, stopped. I mean, what I was trying to say is that you cannot really say on and off in this kind of problem. What we had to do is to put a smoothed step function for both of them, and they are stopped in the same way. So what they do is that the binary just leaves on the point of the step function at which it continues accreting a little, and it stays there, but still it manages to reach coalescence. And I mean, we tried different, kinds of step function, how steep they were, but the results were all in this direction. So I think the result is pretty solid in this sense.
Okay, okay, no, now it's clear. Thanks.
Great, great stuff. I hadn't I'm new to the accretion disk physics stuff. I previously did like stellar mass astrophysics. And this whole idea of they can actually out spiral hadn't appreciated previously, and wondering how much does it I think I had a couple questions, I guess. Trying to remember, but did you show, I think you showed mass ratios equal to 1, like equal masses? Lisa, was there a strong dependence on the mass ratio, or is it not?
Yes. No, this is an interesting point because I mean, this whole thing was developed for mass ratios, let's say above 1 to 10. So 1 to 10 to 1 to 1, basically, because the evidence of expansion is only in this kind of mass ratio range. So it wouldn't make sense to really go in a different range. But what I tried, actually, we tried before, publishing all these results, is that we tested the different mass ratios and the prescriptions for the change in the mass ratio together with the mass accretion. But since most studies seem to predict that there are like analytical expressions to model that the secondary black hole, so the lower mass, accretes more than the primary, what would nearly always happen is that the binary would get equal mass very soon. And so the evolution was nearly the same as just, investigating the equal mass case.
So, but it would have to accrete a lot of mass potentially.
Well, if you are 1 to 10 mass ratio, it's, I mean, at most you grow by an order of magnitude. Of course, I mean, the point is that all this model, I mean, the expansion according to our result would only occur if the mass accretion is very large. So of course, the secondary is going to grow and become as large as the primary in a very short time. Of course, if the accretion rate were much lower, it would take possibly much more time. But at that point, according to our modeling, you won't really have an efficient expansion because the stellar-driven hardening, which always shrinks the binary, is going to be more efficient, and you never really expand the binary. So you don't encounter this problem.
Gotcha. Maria, go right ahead.
Lisa, can I ask a follow-up to that? It seems from what you're describing that it's only for a tiny part of the parameter space that we end up with the situation that the gas is pushing the binary outwards. So it shouldn't be like a second round of the final parsec problem caused by the gas now.
Yeah, so actually maybe it's good maybe if I recap a little bit what because I guess for most US people it is impossible to follow. So the idea of this thing we did was exactly to understand what you just mentioned, Maria. So if you have in some configurations the expansion, whether you have a stalling and then you cannot enter the Lisa band. But so what we did is to combine this gas-driven expansion that is observed in some simulations with stellar-driven hardening that is always found to instead shrink the binary, and also gravitational wave emission that we know from many years would shrink the binary. And basically putting together the very simple equations that govern those processes, we were already just analytically able to say that in order for the binary to expand at some point, we need it to accrete a lot, and in particular, at least above 10% Eddington, depending on the mass. For lower black hole masses, binary masses, even above a 50% Eddington. So you need a lot of gas there to be accreted. And for if you are not accreting as much, basically the stellar driven hardening and then gravitational waves always are larger in their effectiveness of shrinking the binary. And so, I mean, even if gas, of course, is dramatically important for the counterparts, according to our study, it's not really determining the evolution and not, hindering the spiral. And the idea is that even when you have gas expansion, so you have a lot of gas being accreted, the binary may outspiral for a little bit, but in this outspiraling, it accretes so efficiently just because of what I said before, that at some point the gravitational waves become strong enough at the scale at which they are basically stalling at the binary vertice anyways. And the time scale of this whole process, even with the gas delaying everything, is like at most more or less an order of magnitude longer than if gas weren't there. That's
okay.
More or less the summary.
So I guess it's not cause for worry. That's the bottom line.
Yeah, exactly. The bottom line is that, yes.
Looks like Alicia has dropped a comment. Feel free to say yourself.
Okay, so my voice, hello everybody. My voice today is a bit low, so that's why I wanted to avoid speaking. But no, I was just I wanted to add on Elisa's answer and say that that binary expansion is really seen, has really been seen to occur for geometrically thick disks. So I'm talking about like aspect ratio of about 0.1. And while for like this that we expect in like AGN-like, the binaries have always been found to shrink as a result of the gas interaction. So yeah, to answer to you, Maria, I don't think we should be too worried about gas expansion.
Great. So that was basically my next question is how much did the outspiraling depend on the other disk parameters? That answers to that question. I guess I was wondering also, before we can let you off the hook, Elisa, it looks like the time scales are long enough, and if the gravitational wave and if this if the scale is sufficiently small to a gravitational wave emission so to dominate, I don't know. It'd be an interesting. It have interesting, because outspiraling have interesting implications possibly for the spin orientations. Generally, as they're inspiraling, those torques from the companions are getting stronger. The tidal perturbations from companions are getting stronger. But if you're instead outspiraling, those are getting weaker, and potentially maybe less likely for the stuff I was talking about, like the disk breaking. Maybe that's less likely to happen. Could potentially mean that there's more systems being aligned. I don't know. I think I looked through your paper quickly about this.
Okay, yeah. I think I'm not the most expert in the audience to address this point because I don't really do simulations with this. This was a very simple model. So maybe someone else would like to jump in.
Any takers? I'm fine with just floating my ignorance for now and shooting an email or two.
I'm sorry, can you repeat the question?
Sure.
I'm not sure I have understood your point.
Absolutely. Just wondering about the effects that this out spiraling could have on the spin orientations and the spin magnitudes of the black holes in the binary. Since if they're out spiraling instead of in spiraling, that would have implications for the Bardian-Pedersen effect and whether systems are being aligned or not, or if the accretion disks are likely to break and do even more exotic things. It seems less likely to me that the disk would break if the black holes are getting farther away from each other because they won't perturb each other's disks as much.
Yeah, no, exactly. That's one thing that I would expect. Like if they are drifting farther away, then it's harder to get them to break. That's for sure. As for so therefore, I mean, if you assume that if the disk, the circum black hole disk doesn't break, then if you assume that if it doesn't break, then it aligns, then yeah, it might have also implications for spin alignment, I would say. But however, I'm not 100% sure that alignment occurs unless the disk breaks. Like that's, I know that Davide and other people have done some work on this, but yeah, but I'm not like super familiar with the investigations on this particular topic. So perhaps you know more about it.
For sure, yeah. I presented earlier. You probably missed it, but I was basically using Davida's and people he worked with, the model they made for this, and it's got me thinking. I don't know if you could just, I mean, it's definitely not a simple thing, but just I guess naively, the time scale is still long enough over which this out spiraling happens. I mean, you can still have alignment of the spins, I think. The separation isn't made too large. To produce like another degeneracy in the parameter space. Because you'd have binaries who are doing out spiraling and not having a disk break, but still having their spins aligned. Maybe for masses and spins that different, same masses and spins with different editing fraction as those actually in spiral. And do other disk break.
Yeah, and also it's not, as you said, it's not straightforward to understand it and to make predictions. And as far as I know, the simulations that exist have mass ratio of 0.01, if I'm not mistaken, that study, the disk breaking and stuff. So like deriving some results in an equal mass binary case, I don't think it's super straightforward, but it's interesting. It would be definitely worth looking into.
Absolutely. I had a very vague question. As I said, I'm new to the accretion disk business and to massive binary black hole mergers to be in general. And I wanted to ask a really vague question without starting any fights. But merger rates are incredibly uncertain for these supermassive binary black hole mergers. Others have already talked about. I'm just wondering, what are the, I guess astrophysically, what are the major hurdles in terms of modeling and understanding for trying to make more accurate predictions of the merger rates? Somebody have a strong opinion about that?
I mean, my own take is that there are just so many uncertainties. It's kind of hard to point at which one is the biggest factor. So, I mean, there could be uncertainties in the masses of massive black holes, if there's bias in host galaxy scaling relations, the time scales of galaxy mergers, especially at far away from equal mass galaxy mergers, the stellar scattering phase, the impact of large perturbers, the disk effects. Yeah, I think the list kind of just goes on and on. I guess my personal guess is that actually the aspects of the galaxy merger rate, kind of the dynamical friction phase, is probably the biggest impact to the overall uncertainties.
I guess I'll follow up. Do you think, Luke, that there's like a hierarchy in that sense of things? I'm sorry, Marta. I'm just gonna ask this. Do you think there's like a hierarchy of?
No, please continue. I can wait.
Okay, thank you. I think there's like a hierarchy of things. Kind of like what you just said. There's a whole laundry list, but in terms of things that are actually addressable on a human time scale, this is like a hierarchy of things that could actually be addressed, and also solving this problem.
Yeah, I mean, I think there are a lot of different kind of possible avenues to look at. Something that I've been thinking about recently is really trying to specifically match the simulations to observations of dual AGN as a function of different separations, different inferred masses, just trying to use whatever observational constraints we have, which are pretty slim, but really try to use those to constrain the existing models. I mean, at the same time, I think a framework like holodeck that we're trying to develop in nanograv, it would be very well suited to trying to address the question of, exactly how much do each of these different uncertainties, how much do they affect the resulting gravitational wave signal occurrence rates, with gravitational wave background properties, things like that. But yeah, I'm sure Marta has a lot to add.
Go right ahead, Marta.
But basically, I agree. I mean, but I just wanted to add that going back to what we started with, when we go to galaxies in the PTA regime, I mean, the models are not incredibly discrepant within a factor of a few, mostly because at least the models reproduce the galaxy properties. So you can get a bit wrong with the time scales, but at least the black holes are reasonable. When we go to the LISA range, I mean, we don't really have observational constraints in that regime. And I mean, I'm sorry, just in these 2 days, we're going back always to the same point. But we have not many constraints on the galaxies themselves, and basically nothing on the black holes. And so, from the theoretical point of view, we can make everything work. It is very hard to rule out models. And so besides them, so all the uncertainties remain there and we cannot get rid of them. And so to me, this is one of, besides all the lists that Luke has already made of the things that we don't know, and we also have, it's very hard to constrain them in any way. So going back to what Maria said earlier, so I think that with nanograph, the ground and eventually the detections, we will be able to obviously to limit even more there. But for LISA, at the very least, to get, so I'm very, for instance, I'm a big fan of JWST for its own reasons, but also because an instrument like that will start probing better, hopefully, low mass galaxies, low mass AGN. And although we cannot perhaps improve the merger rate per se, at least we can improve the black hole modeling. And so it will kind of help a little bit. I don't know. I mean, I'm hopeful.
Lisa is still out another 10 years away. We have to remain hopeful. Cool. Thank you. Thanks both of you. Maria, go right ahead.
I just had a comment on what you just said. Like, even if we don't make progress in the next 10, 15 years, Lisa will answer these questions. So this is extremely encouraging and hopeful for me. For astronomy timescales, it's not that large.
Yeah, but you're an observer, Maria. I mean, we theorists have to, to earn money by making predictions before things happen.
Exactly. So you can make all the different predictions.
Oh, that's how I earned my money in the last 20 years. I remember when I was doing my PhD, someone said, this is science fiction. It's not science. So why should we listen to you?
That's brutal. Only the observers keep us honest, right? Okay, cool. Okay, we got some time left. I had a couple more random things I wanted to ask a group of experts. This group of experts, rather. You'll have opinions about what the strongest signature of environmental effects, probably specifying to like gas accretion, not like scalar fields and other exotic things. But what do you think would be the strongest signature of an environmental effect on supermassive black hole mergers that Lisa could see? I obviously think the spin orientations will be quite informative, but I'm interested to see what other kinds of things. Maybe there's some parameters that are specifically affected other than the spins in certain ways. If not, it's okay. Don't feel like you have to answer my questions.
I can add some random thoughts to it, I guess. Like one of the things in the PTA band that people that are a little concerned about is that the gas would, or the interaction with the environment would sweep the binaries through the lower frequencies quicker. And this would deplete the population in the sensitivity region where PTAs are most sensitive. But I guess this is not an issue for Lisa, because I guess just because we're looking at the in-spiral views, is that right? And also, I guess the gas, like we were saying earlier, is the effect is to expand the binary. Yeah, I'm showing that I'm not totally. And also, it's individual sources.
Was that for individually resolved sources, not the?
So the PTA issue is for the background.
Background, got it.
I think very quickly, I think I agree with you. It's not so much of an issue because the gas, say it pushes it to the gravitational wave regime, Lisa will probe the final stage. So it's not like, what are you thinking about the background removing power from the lowest frequencies? I think it helps rather than it hurts.
Okay.
But I think for kind of the similar reasons, ultimately it will be very hard with Lisa specifically to probe environmental effects, just because you're seeing that last stage that's entirely gravitationally dominated. So, I mean, I think your point about spins is a really good one. I mean, that's a lasting imprint of the previous evolution that will be seen during the in-spiral and final coalescence. I mean, yeah, maybe some way of looking at electromagnetic counterparts might provide some hints, or the host galaxy, but I think it's going to be extremely challenging.
So look, I was thinking that the most recent thinking on this is that the gas can follow the binary evolution all the way to the end. And if it's not like periodic accretion, probably you will have some gas tied to the individual black holes. So you should expect to find counterparts, and that also helps with the interplay with the binary and the gas.
Yeah. So I think, the current thinking is that there will still be accretion, but even though there's accretion, there's going to be so little total gas mass in the inner region, it's not going to affect the dynamics very much. It's my understanding. So I think there could very likely be an electromagnetic counterpart, but there might not be significant changes to purely gravitational wave driven in spiral. I guess my concern about the electromagnetic counterparts is finding them. So if we're looking at 10 to the 6, 10 to the 6 solar mass system, even at Eddington at higher redshifts, that's going to be very hard to identify, and especially to be able to distinguish that from some other random AGN flaring or variability. So yeah, personally, I'm very concerned about electromagnetic counterparts for LISA sources.
Well, the problem is that the sources are relatively dim because they are lower mass, but and that's another general question I probably have for the group. What is the range of redshifts where we expect to find electromagnetic counterparts? Because we will detect the mergers out to redshift, whatever, 20, but the counterparts, maybe they're more limited to the local sources.
Yeah, maybe I can comment on that. Alberto's here. But at some point that camera should look at me. Okay. So, well, typically the redshift distribution that we expect for the counterpart, very easy. So it should extend in principle up to redshift 6. Okay, it depends a bit from our rate, maybe. It depends a bit on the assumption of the electromagnetic counterpart, clearly on the type of instrument that you assume, but in principle, for example, you can reach a redshift 6.
So is that based on simulations or cuts given the sensitivity of telescopes that we will have in the next 10, 15 years?
Yeah. We took a population of emerging massive black hole binary from the semi-analytical code developed by Enrico Barause. The advantage of the semi-analytical code is that you have the information on the emerging massive black hole binary, but you also have the information. Let's say you have information on the amount of gas that surrounds the binary. So we took that amount of gas, we computed the electromagnetic counterpart, and then we basically look at different portions of the electromagnetic spectrum, so like optical, radio, and X-ray. And well, if you combine all of that, more or less, you can reach a redshift 6 or 8. Depends a bit from your assumption. If you include, for example, obscuration or other stuff, but in principle, you can reach a redshift 6, I would say. At least according to my model. Then probably if you go to someone else with other type of counterpart, the answer might change.
Okay, that's encouraging at least.
Great. I had another random thing to throw out into the arena. Again, I'm not the most knowledgeable person about these things. Feel free to tell me this is ill-informed, but from what I can see, kind of lower mass black holes, like intermediate mass black holes, especially at high redshift, will have likely accreted in like clouds of gas, and not symmetric, but more for like incoherent accretion, whereas more like LISA sources will be accreting probably from disks, involving the disks. But is there some transition there in the, as a function of redshift and mass between, let's maybe make perhaps more well-defined what intermediate mass and massive black holes are in terms of their astrophysical environment? People aware of like a transition between these different kinds of accretion? Naively, I'd expect it to depend on the mass.
Sorry, can you explain when you said accreting from a disk? You mean an accretion? So you mean moving from a spherical accretion Bondi-like to an accretion disk? So a Shapiro-Sunyaev type?
Yeah.
Ah, okay. Very good question.
It's because if you, I guess if you track the evolution of some intermediate mass black hole as like a light seed or supermassive black hole at later times in the age of the universe, I would expect there to be, if it's accreting the whole time, I'd expect there maybe to be some transition, maybe as it's evolving through more or less, I don't know, different astrophysical environments. Maybe some that are more massive. Maybe if it's too massive, if it starts too massive initially, maybe it doesn't ever do. It just does one or the other.
Everyone's shaking against you.
No worries. No worries. I'll...
No, to be honest, I think that it's just too difficult a question for,
okay.
for an answer. In 5 minutes, it may take a PhD to look to the end of a question like that.
That's fair. Okay, I can be satisfied with that, at least for now. Another random curiosity. If someone else has a question, feel free. I don't have to hog this. Does somebody else have a question right now? Well, I got their chest, burning a hole in their pocket.
Not from here, I think.
Okay, Maria.
I can ask a very generic question. What people are most excited that will happen between now and when LISA flies that will be helpful in constraining what we expect from LISA? I mean, you can use your personal biases.
What we think will happen or what we hope will happen?
So I just want to mention that someone in the room mentioned a permanent position.
Yeah, Luke, go for it.
Personally, I think JWST observations of high redshift AGN and quasars will be extremely informative, just to tell us how many lower mass AGN are out there, especially at these higher redshift regimes, or that we're expecting there to be much more lower mass galaxy mergers. So hopefully that'll be really useful.
Maybe I can. I mean, I have my favorite thing, let's say, which is, I mean, I don't know. Probably there is going to be a lot of tidal disruption events detected in the next years, especially, I guess, Vera Rubin LSST is going to really like enhance the catalog. And I mean, my hope is that with that, we are going to really have a better understanding of the black hole mass function also at the lower mass end. And this hopefully can really help us with LISA, even if I don't know in detail all the observational biases that may enter this.
I had a curiosity. I guess it's kind of similar in spirit. The multi-band stuff that Ricardo and Antoine, Chris, and the group here worked on that Ricardo presented today. Kind of an analogous idea, I guess, because there's the decihertz band. There's like the gap in the thing between the LISA and the LIGO, and hopefully eventually we'll have something like DeciGo or Tiango or something like that. I was wondering, I don't know, in terms of trying to understand the effect of environmental effects on the waveforms. I don't know if the decihertz band would be able to reveal more of the in-spiral, especially for the higher mass ones that we have more of electromagnetic data for being able to match those up. That's probably a bit too. Is that just a silly idea, Ricardo?
Well, I wouldn't say it's a silly idea, but I have to say that I had a similar idea this morning, so I have not thought about it for a long time. At the moment, I'm staring at my desktop where I was looking at similar scenarios where we can use Decihertz detectors in multiband, conjunction with LISA for different masses, of course. I don't know. I mean, do you have a specific effect in mind that can show up in the waveform? Or is it like a very broad question, which would require another PhD student?
Well, I love these broad questions that nobody can answer. Well, I know there can be like dephasings that happen to the waveform if certain kinds of, scalar fields happen to exist in the universe, but that's exotic. I don't know if similar kind of dephasing can happen to the waveform. Maybe that. Yeah, go ahead, Martha.
No, exactly. So this is an excellent point, because I keep on, I keep on being confused by all these dephasings. I mean, I know nothing about all this. Just please bear with me and forgive me if it doesn't make sense. But I'm, now it's very fashionable to think of dark matter spikes around black holes, and rethinking dynamical friction in that context as well. And then there are also, the case where you have actual normal matter there. So my basic question is, how could different types of dephasings be distinguished? So can you distinguish whether you have a super Eddington black hole or a dark matter spike just from the radiation wave signal?
I don't know if you had Anton said, I don't know.
Yeah.
Okay, thank you.
I mean, I don't have much of experience with signals. But I mean, a wild guess for me would be that in general, with the phasing, you can have many morphologies. So I wouldn't be surprised if two completely phenomena would give the same morphology over so many cycles, right? But
yeah, it depends on so many factors. Yeah. Yeah, I really don't have much of a grasp of it.
So I guess that one should just model them and see how it goes.
Yeah, I mean, as far as I know, it's probably an open question.
No, yeah, basically my question was, I mean, should we continue thinking about this open question, or if all the model, if there is too much degeneracy, don't worry too much about it. Okay, no, I see your face. I will stop here.
I mean, should we stop thinking about specific problems? I don't think we ever should, in general. But yeah, how much specific effects can be reported or not? Yeah, you really have to do a detailed study for to answer that question.
Yeah.
I don't know.
Yeah, I don't know either. I was in a workshop in Rome last week, and there were tons of talks about this dephasing and exotic matter fields, and nobody talked about distinguishing these things. I think it was just not too helpful. I don't know, I guess naively, I'd expect maybe there could be like a difference in the rate at which these things would be phased, and so you have some way of comparing the offset between two different models. But you see what you'd expect from like vacuum GR, then look at the quality. I think this goes until 1800, right? I think we give people a chance to rest, stretch your legs and nuts.
Yeah. So the plan, I believe, is for the other rooms to come back to this Zoom call, and this room physically, and do like a quick, like a recap summary of what everyone was talked about.
Wonderful. Alrighty. With that, I'll let y'all get on with it. Thank you very much for the discussion, y'all. It was very informative for me. Very fun.
And I guess also to plug for tomorrow, because we have again a discussion session. So homework can be to think of more questions that might need a whole PhD to answer. Thank you, Nick. Everyone.
A great pleasure. Okay. Bye, everyone. Hope I'll see you in the future sometime. I'm sorry I couldn't be there in person.
See ya.
I'll see you soon, Antoine.
Hopefully.
Yeah, hopefully.
Can you guys on Zoom hear me?
Yep.
So we are now all back together, but we are a little bit tired here because it was a long day. So we will be short and won't keep you to, leave you to your business as well. I guess the most interesting thing to see how was the discussion about the projects and what people managed to do so far. I can briefly say something about the stellar binaries. So I guess we can call it a success because we managed to find at least one volunteer to coordinate the project, and we decided that we should have at least 2, but possibly 3 project coordinators. Very likely this will be postdocs. Yeah, and another caveat to that, also very likely they should be the first authors of the paper that will come up of the project. Okay, what else? Then give me a minute, I'm not prepared. Okay, so as a first task, we probably have to do a little bit of a review of the literature, and we started to put together some papers on the list that we should look at. And as a big step would be to decide to run some binary population synthesis simulations when we, in this intermediate step, when we decide what are the reasonable parameters to use. We will probably take something very simple for the, for instance, star formation and the Milky Way, because we would like to compare the how the codes propagate to the double compact object. And the idea is that we compare at every evolutionary stage in the relevant parameter space, TBD. Then, yeah, I think that's it. And we will have to get in touch with some LISA data analysis experts who will be helping us, because the important point that I forgot to mention, thinking from the consortium perspective, probably a very interesting result for everybody would be to see the uncertainties on the predictions of the galactic for a ground background. So that seems like our first possible plan. And yes, so we will get in touch with the data analysis expert for a ground estimate procedures. Yeah, that's it. We already have a Google Doc and people signing up and blah, blah, blah. Next project.
I can briefly review the massive black hole one. So we also have made good progress, I think. So we don't have coordinators yet. We discussed that people should volunteer and perhaps think overnight about it, because first today we discussed what the project is about, what tasks are involved. So coordinators should, at this point, know what they sign up for when they volunteer. We created a Google Doc, and unless I hear objections from the room or people online, I could email all the people who signed up for the project. Not everyone was present today with this Google Doc. So if you have objections, please raise them now so that I won't send the email. So we discussed how to proceed, scientific ideas, what people could be doing based on their expertise. And we concluded with a bullet list and a table, bullet list with people adding their expertise, and a table that includes the databases and catalogs that we can work on. So my basic question is if there is any objection to sharing the Google Doc that we created with the rest of the people who signed up for the project.
I think that's a good general question for all of the projects. We probably should make that same request of everyone who was in the binary section. Also, not everyone was present who signed up, so.
Yeah, I think in general, it's a good idea. We should do it.
Okay, so have the blessing to send the email. Thank you.
I say something about number 3. Can you all hear me? So for project 3, I think we made good progress. We essentially made a plan for what we call option 1, so for the injuries in disks. So we have already a structure of how the code comparison should be done, what are the setups that we want to start from. We have a list of 7 codes that we put down. On a Google Doc, we have a description of the setup and of the codes. And of these 7 codes, we have 5 codes that have already someone is down for each of them. For the other 2, we have an idea of who could be interested, but we have to reach out to these other people. Now, one thing that we discussed at some point was that for example, for these 2 codes that don't have an assigned person yet, it's not clear whether we will find someone necessarily inside the consortium or inside the working group. And so I think an option is to reach out even outside the working group if there is someone who is interested. But on this, I also would like to hear the opinion of people from the other groups. Do you think is it fine if we think that there is one code that needs to be in the comparison, but we don't have anyone inside the working group that can actually join for that code? Do you think it's fine that we reach out outside the working group, or is it making it too broad? I don't know, especially Shane and Valeria. Martin.
Yeah, I was going to ask, is that a question, Lucio? So, yeah, I mean, we had folks in our discussion who aren't in the consortium yet. So I think at this level, here as we're starting, that we're certainly open to that, especially if we need the expertise to accomplish the project. I think my general feeling, we shouldn't worry about it too much, but we will have to cross that bridge eventually, depending on what kinds of involvement with the consortium happens, right?
Yeah, so I was thinking the same, that for now we should not think that this is a problem, but eventually later on.
Yeah.
So I go ahead.
The general philosophy traditionally has been that the barrier to associate membership is very low because you don't have to commit to definitive work. So if it did become an issue, I think the assumption is that we should advocate for associate membership for these folks if they don't object.
Right, exactly. So yeah, we can use it also as a way to push them to become new members, basically.
Well, I don't think we want to push them towards membership, but the central issue in the consortium is that because we're approaching phase in mission development where we talk with our industrial partners, there's proprietary information they don't want shared outside the consortium. So if you're not a member of the consortium and you're exposed to proprietary, that's where it causes problems. But for this sort of work, I don't anticipate it being a problem. That's just what the discussion will be around. So
yeah. So anyway, the Google Doc will be sent to the other participants who are not present, so the ones who expressed interest in the code comparison but were not able to be present. And yes, so then hopefully we will find other people who will assign themselves to the course that still need assignment. Yeah, so we'll take it from there basically, by sending out the Google Doc. The coordinators are not assignments. Only the code responsible, but not the general coordinator.
I agree with Shane.
You didn't have to.
I'm genuinely agree. So
I assume Marta also agrees because she didn't comment on it.
Yes, Marta agrees, she says in the chat.
Okay.
okay, so then I guess this was a successful day. We did some good LISA science and we heard amazing talks. And really, I want to thank again all the speakers. It was exciting to see your results, but also all the work that you put into presentation to make the nice figures, to make a good presentation. Thank you all. And yeah, we can applaud.
And I just want to add also thanks to all the chairs who guided us through the sessions.
Yes, thanks everyone.
Thanks for the chairs. And tomorrow we restart again.
It never ends.
Okay. Have a good rest of the day.
Goodbye, everyone.
Bye.
Bye. Bye.
Bye.
Bye.